the speaker hardly needs an introduction, but customarily I will again give a very short one. So it's very nice to have Andreas Heinrich here today. And let me very briefly introduce him before giving the floor to him. So Andreas graduated with a PhD from University of Göttingen, and then after that moved for a postdoc at the IBM Almaden Research Lab with Don Eigler. And then there he stayed there after the postdoc and to become a research staff member, and then also the group leader of the magnetic nanostructures on surfaces and scanning probe microscopy since 2005. And after a little bit more than 10 years there, in 2016, Andreas moved to South Korea to set up and to become the director of one of these institutes of basic research. His institute is called the Quantum Nanoscience. And he's also a professor at the actually, I don't know, is this an acronym or a word, but the EWHA Women's University. Okay, and I think everybody knows Andreas's group, first at the IBM and now at the IBS Quantum Nanoscience, that they have been the pioneer and the world leader in the spin excitation and single atom spin resonance spectroscopy with scanning tunneling microscopes. And I think today's colloquium we are going to hear the latest on this. His title is Electron Spin Resonance of Single Atoms on a Surface Observed with STM. I think with that, Andreas, please, looking forward to your colloquium.
Great. Thank you very much, Peter, for the introduction, but also for organizing this colloquium. I've enjoyed many talks, not everything live because sometimes the time difference was not right, but I watched everything on YouTube. I think that combination of live and YouTube is perfect, so please keep that up. Gives everybody a chance to participate. Also, on a personal note, I want to say that this Corona crisis has been terrible and great. Of course, it's terrible for all of us for many reasons, but it's been really great for me personally because it allowed me to spend a lot of time in the lab. So the last 4 months, I've actually been a real postdoc, working day and night in the lab, and that's, I have to say, I really, really enjoyed more than being a director or something like that. So, having said this, let me get started here and turn on the pointer. So today I want to spend the vast majority of the time on electron spin resonance in STM. So one slide, a little bit of introduction on what kind of materials one can study and what we do here at QNS. We have a small effort right now on point defects in materials, particularly nitrogen vacancy center in diamond. We have a large effort on atoms on surfaces, and we have a growing effort on tailored molecules with good quantum properties, such as this endohydrofluorine that you see here. Now, we want to do quantum science, and for me, that means we have to start with discrete energy levels. For spins, of course, you can also have the more classical, continuous energy level diagrams that you might know from nanoparticles or from thin films. But we really want to go to the discrete energy levels. And then moreover, we want to use the more advanced techniques such as CW electron spin resonance. Here, one of our measurements, not with STM, but with an ensemble averaging ESR spectrometer. And then finally go for pulsed ESR, which then takes us a big step towards really coherent control of these quantum states towards quantum coherent functionality. And today I really want to talk only about atoms on surfaces, and then start off with the quantized energy levels, walk you into CW electron spin resonance, and then end up in the pulsed ESR schemes. Okay, so I also, because we are all experts in this field, I want to talk a little bit more technique than I normally do, sort of nuts and bolts kind of things. As an introduction, I'll show you results from 3 STMs here. 2 of them here at QNS and one of them, the one at IBM that I've been using. Oh, Peter, by the way, I did stay at IBM for 18 years, not 10 years. So that shows you how old I am.
Yeah, but okay. But you were the group leader only for 11, right?
That's true, that's true. So they all operate in ultra high vacuum and at low temperatures. We have variable, 3 different types of low temperature systems, but they're all combined. Let me put on the pointer here. They have the STM in the bottom of a bath cryostat. So this makes it a little bit inaccessible, the STM being down here. but it is surrounded by a cooling mechanism that takes the system below 4 Kelvin. Now we have a single shot helium-3 system, a unisopo system that goes typically to about 0.4 Kelvin. The IBM system typically running at 1 Kelvin, and then a new system, a millikelvin one, that can go down to 10 millikelvin. And then they all have magnetic fields that we can control. We like to have 2-axis magnetic fields, so they have a magnetic field perpendicular to the surface and in plane of the surface. And nowadays for our studies, it's not so much the maximum strength of the magnetic field. So 1 Tesla for us is usually enough, but we want to have this multi-directional magnetic field. Okay, so let me start the model system or the system that we'll be studying today, which is single atoms on a thin decoupling layer on a metal surface, which many of you have heard me talk about for a long time. If we start with the simplest one, spin 1/2, then we only have 2 states. We apply a magnetic field, we split off the ground state from the excited state, and the energy difference between those is the Zeeman energy, which has one parameter, the G factor, which shows us the strength of this interaction and is proportional to the external magnetic field B. Now, we work on double layers of MgO, and so here you see an STM picture, 30 by 25 nanometers, taken with our Bob system, where we have here an area that is bare silver, 100. On top of this, you have titanium atoms and iron atoms. Titanium atoms happen to be taller here. Then we have 2 monolayers of MgO. You can easily see this because we put a lot of defects on there. And then we have here 3 monolayers of MgO. And on top of this, of course, we have our atoms, such as this titanium atom on the bridge binding site here. We do the sample preparation in a moderately simple process in the room temperature vacuum chamber. We then transfer the sample into the STM, where we then deposit the atoms at low temperature and also do all the imaging and spectroscopy at low temperature. Now I want to show you 2 atoms today. One of them is the titanium. Attached with the hydrogen is a spin 1/2, so relatively simple, only 2 states. The second one is the iron atom, which has a slightly more complicated or interesting electronic configuration. So we are in the 3d6 configuration mostly. And in the 3d6 configuration, before spin orbit interaction and crystal field, you have S equals 2 and orbital moment L equals 2. So this one has 5 states, this one has 5 states. So together you have 25 states in the lowest energy multiplet. Now, on top of this, of course, we have the spin orbit interaction, but also we have a strong interaction of this atom to the binding side. So here I show you an iron atom sitting on the oxygen binding side, oxygen here in red. And you see that this is negatively charged ion. And then we have positively charged ions on the side. So we have a fairly strong electrostatic interaction, so-called crystal field, and that changes our energy landscape dramatically. Okay, so long story short, this iron atom on this oxygen binding site of MgO, the lowest 5 states of those 25, they form one multiplet here shown with strong easy axis magnetic anisotropy. So we have 5 states, we label them with the SZ quantum number -2, -1, 0, 1, and 2. And we have the case where the plus and minus 2 states are the ground state, and they're separated from the first excited states here, plus and minus 1, by a 14 millivolt energy excitation. We have, because we have 4-fold symmetry, we don't have this E term, the first order transverse term as x squared plus sy squared. We only have sz squared. And so this is relatively simple energy diagram as shown here. Now, when we look at with the STM, then we can see 2 strong spin excitations at -14 and at +14. Here, this is just tip features, so we can ignore those. And those are the spin excitations from this, when the spin, the iron atom is going from the ground state to this first excited state, either on this side or on this side. They happen to be the same at 0 magnetic field. Now, for those of you who don't know what spin excitations are, why do we see a stepwise change in the conductance here? Now, you've seen me give this diagram many times before. I like the way to explain this in the following way. We have fill states on the tip. We have fill states on the sample, and they are separated by the vacuum barrier. So this is here our 4 or 5 electron volt high vacuum barrier. In addition, we have an atom or an ion sitting here that has a discrete energy difference between the ground state and the first excited state. And so now if I start increasing the voltage between tip and sample, then I'm shifting the Fermi energy down of, let's say, the sample, and I get a constant conductance until I get to the point where I have enough energy to make one spin excitation and kick the iron atom from the ground state to this first excited state. At that point, I change the conductance because I open up a new tunneling channel, and in the iron case, it gives rise to an increase in the conductance, and then a further increase of the voltage gives more and more electrons that can make this excitation. And so you can see that's why I believe we see the stepwise change in the conductance, symmetric about positive and negative voltage. Now, this is not so difficult to see for iron because it's 14 millielectron volts, but generally these IETS steps are broadened by 5.5 kT, and so you have to never an infinitely sharp step, but you have a step that is broadened at least by the temperature, maybe also by your AC modulation or by other effects. Okay. So if we apply a magnetic field for iron in the out of plane direction, then we can shift the energy difference between the ground state and this first excited state here. And essentially for the rest of the talk, I will only think of the iron as having these two states. I will ignore essentially all of these other states because they don't really play a role for what I'll be talking about. Interestingly though, if you apply a magnetic field in plane for iron, this out-of-plane anisotropy is so strong that it doesn't care at all about this, and the energy between these two states stays the same, even though you might apply 1 Tesla of in-plane magnetic field. So we have a very, very strong direction dependence of the direction of the magnetic field for iron, but not for titanium, which is a spin 1/2 and therefore doesn't have these anisotropy effects. Okay, so that always sums it up basically. I want to just show that spin excitation spectroscopy, we can measure the Zeeman energy, which here is the spectrum for spin 1/2, the titanium atom on the oxygen binding site. You see this little feature here, that's the spin 1/2 excitation measured with a spin polarized tip. We can measure the magnetic anisotropy, which I showed you for iron. We can see Kondo effects if the spin interacts with the underlying conduction electrons and is amenable to Kondo effect. We see the Kondo effect. We don't show this here. And we can combine this whole thing with atom manipulation that we've done for many, many years to build quantum spin chains or spin lattices or more complicated structures. You name it. I think it's the beauty of STM that we have in situ characterization, manipulation ability, and spectroscopy all in the same tool that we can actually do something like build a chain that has precisely 12 atoms in a particular arrangement. Okay, but today I want to talk about dynamic effects. I want to leave this static picture behind and talk only about the dynamic effects in the following. So there are 2 types of dynamic effects. One I call here incoherent, and the other one I will call coherent. So the incoherent is something that you might be more used to. That's just asking the question, if I kick my system from the ground state, let's say into the state 2, how long does it live in the state 2 before it falls back down to the ground state? Right? This is the so-called energy relaxation process. And in the language I'll be using in the following, this is called a T1 relaxation time, energy relaxation time. You can see for the iron here, we have a special situation because we have an energy barrier that is 14 millivolts high here. So total is about 20 millivolts high. And so it's not so easy for the spin to come from the state 1 back to the ground state 0. Right here I have applied a magnetic field. And so this we can use to measure relatively long spin relaxation times for this transition here. And I don't want to give it too much detail on this mechanism here or this technique, but we can use electrical pulses in the STM where this is our voltage that we apply to the STM, and we replace our normal DC tunnel voltage with a series of pulses. We have a strong pulse, we call it the pump pulse. Then we turn off the voltage, and then at a certain time delta t later, we apply a smaller pump, the probe pulse. Again, we turn the voltage off, and we go repeat this thing 1,000,000 times. Now, if we do this, then we can measure the relaxation process, namely at the time scale delta t of the probe pulse, what is the population of state 0 and state 1? And this is the current that we're measuring if we have a spin polarized tip And then you can see you get beautiful exponential curves. For this particular case here of this iron atom at a certain magnetic field, I don't remember what it was, we have a T1 time of 35 microseconds or so. Right? And 35 microseconds is a very, very long time in comparison to the average time between electrons that are tunneling. And I like to say that if you take 1 nanoamp of tunnel current, that's about 1 electron every 100 picoseconds. Right? So you see 35 microseconds, there are many, many, many electrons tunneling, even if you go down to 1 picoamp of tunnel current. Okay, so this is the incoherent time scale, and we sometimes need to know this. But again, for this talk, I want to skip over this and go to the coherent manipulation. Right? So I want to now introduce this technique called CW, Electron Spin Resonance. In CW spin resonance, you have 3 more timescales that play an important role, and this is a slide I stole from one of my PIs, Yu Chong. We have the first timescale I already talked about, the energy relaxation time, T1. The second timescale is given by the energy difference between state 0 and state 1. So this energy difference can be expressed as a frequency, and that is the so-called Larmor frequency or the Larmor precession. That happens every time that your spin is not in one of the eigenstates, state 0 or state 1. If you are in a superposition state of state 0 and state 1, then you will see precession of the state vector around the z-axis in this model here. This is the so-called block sphere model, which is the easiest way to describe this superposition of states. It has only 2 parameters, theta and phi, and parameterizes this coherent superposition of the wave function. So that's the second time scale, the Larmor frequency. This is basically our ESR frequency. Then we have the Rabi frequency, or the pi time, the time it takes to make a coherent rotation of my spin vector when I apply a driving field. And so if I go from the state vector 0 to the state vector 1, then that is a so-called pi time. And if I go from state 0 into this plane here, that's a pi over 2 pulse, just a nomenclature. And so this depends on how strongly am I driving my field with my ESR driving field. So there's 3 time scales, and the last one that's a little bit difficult to draw in this diagram, that's the so-called quantum phase coherence time, or T2 time. And that time actually means after the T2 time, this superposition of the wave function is not the best model anymore, and you have to go into slightly more advanced models, basically meaning that you have relaxation of your state vector that you don't control with these controlled Rabi frequencies. Right, so those are the 4 timescales that play an important role in ESR in general. Okay, so ESR with the STM, this was an idea that I had together with my friend Arjan Adevan, professor from Oxford, a long time ago. Namely the fact being that we have a strong electric field in the STM. And what if we can make this electric field time dependent? Can we then drive coherent manipulations of a spin using this time dependent electric field or frequency dependent electric field, right? Of course, you want to say that if I am in resonance with this driving with this Larmor precession frequency HF0, then maybe I can make coherent transitions of the spin from state 0 to state 1. Now, what this means in simple cartoon pictures, if I look at the population of how much time does my system spend in state 1 versus state 0, if I'm far off resonance, I'll be thermally populated. If I then sweep the frequency, I can make a change if I get close to the resonance frequency, and maybe if I drive the system really hard, I can get to 50% population at the resonance frequency. And if I have a spin polarized tip, then I can measure this directly as a change in the average tunnel current as a function of the frequency. Let me point out here, in all of I'm talking about today, we are always measuring essentially a DC property, the DC tunnel current, as a function of a very fast changing high frequency electric field. Okay, this is where I normally show ESR traces, but I thought that today I want to show you a little bit on the technical nuts and bolts of this. So here's one of our ESR systems. This is a dilution fridge ESR system, and here's the room temperature part. Here you go from room temperature down to 5 Kelvin. This is a 5 Kelvin flange. from 5 Kelvin, you go down to the mixing chamber, which is at the millikelvin temperature. And from millikelvin temperature, we go down to the STM, which is here, which is all at the same temperature. And I point this out because we have different cabling requirements. We want to get high frequency signals down there, so we need to use semi-rigid cables. High frequency, tens of gigahertz kind of cables. And from room temperature down to 5 Kelvin, we are using silver-coated stainless steel or silver-coated beryllium copper semi-rigid cables. Then we switch to a superconducting cable from 5 Kelvin down to the mixing chamber, because here we don't want to conduct much heat, but we want to have good electrical conductivity. And so superconducting cables are perfect for that. Then we switch from the mixing chamber, which is here, down to the STM, which is here. We want to get a lot of heat down here. We want to use the cooling power of the mixing chamber to cool the STM. So we use a copper semi-rigid cable. You can see it here. That's the copper semi-rigid cable. That goes from 10 millikelvin down to the STM, which is also at the same temperature. And then in the STM, so this is the same, this is this part here, shown here. Then we need to bring this high frequency signal down to the tip. And for this, we need to go to our walker. And so there we have a thin copper flexible, not semi-rigid, but a flexible cable, which you can see here in this loop. And so I want to point out that this is a pretty complicated mechanism how to get this high frequency signal down to the STM. Okay, now then you might ask yourself, how do I know that I really have some high frequency signal at my junction? And this is actually beautiful, was developed mostly by one of my former postdocs, William Paul, who is now working for Apple. Here we have a spin excitation. This is conductance, and this is a sample bias. We see in blue a strong spin excitation at about 58 millielectron volts. This is a cobalt atom on MgO. And you can see this is just one single step with a certain width. But now if we apply a high frequency RF signal here, then you can see that the signal changes to this red curve. And this red curve tells us what the amplitude of the RF is at this particular frequency that we are applying here. Right? This is basically the time that the system, the voltage spends. Most of the time it spends at the turning point. This is the same as in AFM, for example. And so you see that if I go to this voltage here, then I'm sensing this step half the time. The other half of the time, I'm not sensing anything. And so you can see you get a broadened function here. And if you fit this, you can immediately get out the broadening, the amplitude of the RF voltage that we're applying, in this particular case, 4.1 millivolts. And so then we know that at a certain frequency and at a certain power of the source that we're using, we get 4.1 millivolts down at the junction. Right? But now we want to measure this at all frequencies, because you'll see that this transmission is very complicated because of our cabling. Right? And so we don't want to do the same process at all frequencies. That would take a very, very long time. And so we do simultaneously, we do just a lock-in measurement. So now we turn the RF voltage on and off and on and off, and we switch this at a frequency that we can easily measure with our practically DC femtoamp, the bias, the tunnel current measurement, right? And so if my signal is dependent on if my signal is dependent on this broadening here, meaning if I have a strong nonlinearity in my IV curve, then I will see a different tunnel current when the RF is on versus off, on, off. And so then I can measure this delta I just as the output of the lock-in. And so now I have a way that I can relatively quickly measure the amplitude of the RF voltage as a function, for example, of the frequency. This is beautifully described in this review of scientific instrument that William wrote before he left for Apple. And so then we can look at the transmission. So this is the transmission from 5 gigahertz to 30 gigahertz here. And you can see that these are 3 different systems I'm talking about. One is in green, is the dilution bridge that we're just operating here at QNS. Then in blue, we have the IBM, we call that the 1K STM. And in yellow, we have the Unisoku STM also here at QNS. For the Unisoku, I don't have the low frequency transfer function. This is also relatively high as shown here. And you can of course see that as I change the frequency, I get more loss in the system. The cables have some loss that it's just frequency dependent. But that would not be such a big deal. You could easily think about just calculating this and compensating for this. But you can actually see that there are lots of spikes in there. Like here's something about 18 gigahertz, where both the IBM system and the Bob system have a big loss. Or here at about 14 gigahertz, we have a big loss. And so there's something about the connectors and the types of cables that we're using that makes it difficult to do frequency dependent measurements. However, if I have this transfer function, then I can tell my high frequency source not only what frequency do I want, but I can tell it what amplitude do I want in order to compensate this transfer function. I can just invert this transfer function, and then I can make a constant amplitude signal at variable frequency at the junction. And note that every system is different, and this also depends on the helium level. It depends on all sorts of things. So you have to measure this relatively frequently if you want to have a flat amplitude frequency dependent signal at the junction. Right. Okay, so much for the nuts and bolts. So let's look at one of those ESR signals. This is measured with the Unisoku system here. An iron atom on 2 layers of NGO. We have here a magnetic field applied in the Z direction of 0.11 Tesla, and you can see this is the lock-in signal that I showed you before. It's basically the change in the tunnel current when the RF is on versus off. You can see that we get a signal here of about 200 femtoamps change at 12 point something gigahertz if we apply 0.11 Tesla. And now, of course, if we change the magnetic field, then you can see that this ESR peak moves to, in this case, if we increase the magnetic field, moves to a higher ESR frequency. And so the key here is, of course, that we can measure the Zeeman energy as a function of this out-of-plane magnetic field. And now you can see here the difference between these traces is only 10 millitesla. And so you can already see that the energy resolution you get in ESR is much, much, much better than you get in just spin excitation spectroscopy or any other tunneling spectroscopy that depends on the Fermi function broadening. Right? This does not depend on the Fermi function broadening of tip and sample, and therefore we get a much higher energy resolution. I should say that Susanne, who's now working with Sebastian Loth in Stuttgart again, she and William together were the first people to do this first ESR-STM when I was still at IBM. And this is done with either the second or third ESR-STM in the world. It's about 1 year old data. Now for iron, the situation is slightly complicated because this iron atom is a spin 2. I showed you that we have the 2 lowest lying states, SC plus minus 2. So that's not a normal ESR transition. And so we believe that for many tips, it is really good to have an in-plane magnetic field. And so here you can see the ESR signal strength, the amplitude of the ESR peak at a certain fixed out-of-plane magnetic field as a function of the in-plane magnetic field. And you can see for this particular tip, we see no ESR signal at 0 in-plane field, but we do see an ESR signal if I apply something like -2 or +2 Tesla of the in-plane field. Right? And you can see that the tips are a little bit different, and I should point out that the most difficult thing about ESR-STM is to find the right tip. Right? This seems to be the crux of all STM experiments, but it's always difficult to find your right tip and to characterize your tip properly. So some tips give ESR without BX. We have some tips that do this, but most of the tips do need a BX field for the iron atom, not for titanium. Okay. So this indicates here that we have a magnetic field coming from the tip. And I want to now talk a little bit about what the influence of this magnetic field that this tip has is on the ESR or on the magnetic state of the atom underneath. And for this, I will switch to titanium atom. So the titanium here on an oxygen binding site is a spin 1/2 because the titanium has a hydrogen atom attached to it. And together it makes it only have a single electron in a single orbital here. So it's an S equals 1/2 system. Now, if we look at the ESR here for this iron, you can see again, you see here one nice peak at about 23.5 gigahertz. Again, the signal amplitude on the order of 100 femtoamp or so. And now we want to measure this as a function of the tip height. So as a function of the tunnel current. And you can see that if we increase the tunnel current or decrease the distance between tip and sample here, you can see for this particular titanium atom on oxygen that we have a very, very strong influence of the tip sample distance on the ESR frequency. So here we go from 3.6 angstroms to 2.6 angstroms, and we see we go from 23 gigahertz to 27 gigahertz or so. So 4 gigahertz shift in the ESR frequency by changing the tip height by 1 angstrom. So very dramatic. This is different for different atoms. So right now we're measuring a lot of titanium atoms on the bridge binding side. They have much less influence, but this is just the way that the system is here. By the way, I want to point out that this is in absolute tip height measured, 0 angstroms being point contact between the tip and the atom. So this is the ESR range.
For interrupting, there's a question by Igmar. Igmar, please go ahead.
Yes, sorry for interrupting. I was intrigued by what you showed on the previous slide, that the signal strength so strongly depends on the tip that you have. And I was wondering, did you ever try an experiment with tip functionalization, such that you have a very, well, let's say a tip apex defined by, well, in this case, maybe an iron atom, and then you magnetize it in a certain direction? And do you then still see the same type of effects?
So when I say different tips, I mean functionalization of the apex of the tip, right? For example, in the IBM system, I believe we've never changed the tip over 10 years, so the wire is still the same, right? But the apex of the tip, meaning do we poke the tip to sharpen it, and how many iron atoms do we pick up, that we change all the time, right? And so, but it is not at all clear that one iron atom is better than many iron atoms, and it really depends on what spin you're looking at on the surface. So we do functionalize the apex of the tip all the time. That's what I mean by preparing the tip, mostly by transferring atoms from the sample to the tip. But we don't know more about this apex of the tip, right? We don't, that is really the dark magic.
Okay, very clear. Thank you.
Okay, so back to I was just pointing out that this distance here is measured as the absolute height, measured at 0 angstroms being point contact between the atom on the surface and the tip. But the beauty here is that we can then also measure the spin excitation spectroscopy. So here we are at 1.6 angstroms, so not quite connected, but close to this. And you can see that, yeah, maybe we can see a nice spin excitation here. But this spin excitation energy grows dramatically as we bring the tip in closer. So here we're going again about 1 angstrom closer, and you can see that here we have a much higher spin excitation energy than here. This again comes from the interaction of the magnetic tip with the titanium atom on that surface. So the beauty here is that we can put these together. We can extract the total energy, the Zeeman energy, both from the ESR frequency. Here it's just HF nu. HF basically, and here from fitting with the spin excitation spectroscopy I showed you in the beginning. And then we have the energy as a function of the tip height here with a change of tip height of about 3.5 angstroms or so. And you can see that at very far distances, of course, we go to a constant value, and that value is given by the external magnetic field. At that point, the tip magnetic field does not play an important role. But if we come in closer, then you can see that the tip field becomes much stronger than this external magnetic field, right? So here's the same axis expressed as if there was a tip plus external magnetic field, and you can see we go up to about 12 Tesla here at the closest approach. And we can plot the same information, subtracting this value of 92.9 microelectron volts on a logarithmic scale, and then you can see we have a perfect logarithmic exponential dependence of the energy scale with the tip sample distance here, strongly suggesting that for this particular system of this particular tip and the titanium atom sitting on the oxygen binding side, we have a exchange interaction between the atom on the surface and the atom on the tip. But let me point out that every tip is a bit different, and every atom on the surface is certainly different because it depends on the orbitals that you have. But I think it's just beautiful to see this over 4 orders of magnitude. And the message to take away from this is if you do spin polarized tunneling on a thin insulator, then you have to assume that you have very strong magnetic fields just coming from your magnetic tip, right? So here, the spin excitation spectroscopy ends at approximately 1 Tesla tip magnetic field. That's the lowest tip magnetic field that we can measure the IETS for this particular case. Okay, this was work done by Kai, who's now moving soon to take a position in China. Okay, I want to point out, and I'm really super happy about this, that ESR-STM is spreading to other labs. I know of a few labs that now have ESR-STM, but Pietro and Sebastian Stepanov at ETH Zurich, they have published their work just recently. Here, they're using a 5 Kelvin system, a SPECS-STM, and they go to very high frequency because they're smarter about how they apply their high frequency. They make a bias T at low temperature, basically. And so then they can measure between 34 and 37 gigahertz here, the ESR, and this is now measured as a function of the external magnetic field at a constant frequency. So here's a sweep at 34 gigahertz, changing the external magnetic field and seeing when you hit spin resonance. And of course, you can express this also as the usual Zeeman diagram, and then you can also extract the tip magnetic field, just like I showed you before. And here get a magnetic moment for this titanium atom of very close to 1. This is the precision with which we can measure magnetic moments here, right? Much better than we can with normal spin excitation spectroscopy because of the power of spin resonance. Okay, because Jose is our host, let me show you my favorite way that I think that this ESR-STM actually works, because we have an electric field that is driving everything here. So how does an electric field drive the spin of this atom here? Now what we think is happening here is that this high frequency electric field acts on the positively charged magnesium and the negatively charged oxygen and the somewhat charged titanium or iron atom here and moves them around. And let me point out that this frequency, let's say 20 gigahertz, it's much less than vibrational modes that hold this atom in place here. Those vibrational modes are 1000 gigahertz or more. And so this is a very slowly changing electric field environment in comparison to the vibrational modes here. And then if we combine this with the fact that we have a strong magnetic field locally here, then this converts this motion of the atom or the motion of the magnesium and the oxygen into a time-dependent magnetic field, which can then give rise to the spin excitation in a more traditional way. But let me also point out that this is by far not settled. There are several different competing theoretical models, and I think the best we can do as experimentalists is give more data into this field and see what comes out as the best model. Okay, so this was the half of the talk, basically the ESR-STM. And now I want to show you a couple examples of what we can do with ESR-STM. So here's data still from Susanna and Will's original paper. The iron atom on 2 layers of MgO. Here the ESR peak at a relatively low driving field at 25.680 gigahertz. That's the center frequency here, with a line width of 3.6 megahertz. Right, this is about the best that we have seen. We have seen, I think, 2 megahertz was the very best we've ever seen. And let me just point out that this is a super small line in comparison to what you're used to from normal tunneling spectroscopy. If you just translate 3.6 megahertz into energy, you have something in the range of 10 nanoelectron volts energy resolution at a temperature of, let's say, 1 Kelvin or 5 Kelvin. So at least 1,000 times better than what you can do with tunneling spectroscopy, right? And this is true for all resonance techniques, nuclear magnetic resonance or electron spin resonance. The energy resolution, the line width, is not directly to first order related to the temperature, only indirectly related to the temperature, right? So if we now look at the center frequency here, then we have a very sensitive detector of local magnetic fields. And so if we put another atom nearby, let's say an iron atom or another titanium atom, if this atom is far enough away and we do not have an exchange interaction, then we switch to the dipolar interaction. And the dipolar interaction is pretty easy to understand. So this iron atom, if we apply a vertical magnetic field here, wants to point along the magnetic field, and then it creates a its own magnetic field that is anti-aligned with the external magnetic field at the location of the titanium atom on which I want to measure the ESR. And this shifts the ESR frequency down to a smaller energy, smaller frequency. On the other hand, if the iron atom goes into this excited state, it flips its spin and now it's pointing down. And that means locally here, the magnetic field is increased, enhanced, I have a higher ESR frequency. And so if you have such a model where you have a nearby atom having only 2 magnetic states, then you should not see 1 ESR frequency, but 2 ESR frequencies. And here's something that we just did on our Bob system just last week, I think. We have here a titanium atom on the bridge binding side and another atom nearby. We thought it was an iron atom, but now I put a question mark there. I don't think it's an iron atom, it's something else, but it is a spin. And this gives rise to an ESR sweep where we now see 2 lines. Right? Now, some of you will ask me, why is this a dip and not a peak? And why does it have this asymmetric line shape? So let me answer this right away. So whether you have a peak or a dip has something to do with the relative alignment of the tip magnetic moment, the spin polarization of the tip with the spin on the surface. So this can depend on whether my tip has a spin orientation that is aligned or anti-aligned with the magnetic field. And we get this asymmetric line shape because we have a slightly more complicated process of ESR detection. So we have 2 mechanisms, one being the tunneling magnetoresistance, which I've explained so far. But in addition to this, we have a high frequency process called homodyne detection, which gives rise to this asymmetric line shape. But for the dimer, the most important is 2 things. One, we see now 2 ESR peaks, and they're separated here by something like 1 gigahertz. And you see that one of them is smaller in amplitude than the other one. And so this tells you something about the thermal population of the second state. How often is it in the excited state versus in the ground state? Right? This is directly measured here as the relative height of these 2 ESR states. And then we can measure this as a function of tip sample distance. This is now a bridge binding site, and you can see here over almost 1 order of magnitude change in the tip height, the ESR frequency only changes by a relatively small amount, much, much less than what I showed you for the titanium on the oxygen binding site. So this is A, because we have a different tip, but B, also because they have just a very different behavior in the interaction between tip and sample. And so I just want to point out that you don't know a priori how much the tip interaction is with the atom, right? But you can see here, of course, as we go to very low currents, the signal basically disappears, becomes easier to see as we go to higher currents because it is proportional to the tunnel current. And if we now plot what is the center frequency here as a function of the tip height, then we can see a slight change with the tip height. But if I look at the energy difference between these two, that's the interaction energy, then that's fixed and independent of the tip height. In this particular dimer, 1.25 gigahertz. Right? So this allows us to measure local magnetic fields with very high precision and independent of the tip height and also independent of the local structure of the tip. So this interaction energy really is a property of the atom on the surface, the 2 atoms, and not of the tip. So this is actually really beneficial for us. Now, we can measure anything that creates local magnetic fields, including this process here. Now, we have titanium atoms, and you can see that we have most of the titanium atoms having a single, very sharp, very tall ESR peak here at a certain center frequency, let's say 22 gigahertz. But sometimes we see 6 ESR peaks of equal height. Sometimes we see 8 ESR peaks, and this is not the right audience to let you wait very long. So there we see the hyperfine interaction between the electron spin on the titanium atom and the nuclear spin. Now, titanium happens to have mostly 0 nuclear spin. So when we have 0 nuclear spin, then we have a single ESR line. If we don't have any atoms nearby, you see here there's nobody nearby, then we have local magnetic field that is given only by the external magnetic field and by the tip magnetic field. But if I have a nuclear spin of 5/2, about 7% of the atoms do this, then I have 6 ESR lines, equal height, meaning that they're equally populated during the measurement time. This measurement sweep I don't know exactly, Philip would tell us better how long this took, but let's say this takes maybe 20 or 30 minutes to measure this trace. In this time, the nuclear states are equally populated between all the 6 different levels. If I switch to a 49 titanium, then I have nuclear spin 7/2, so I have 8 orientations and I get 8 peaks. Now, of course, we don't know a priori from the STM image or something whether some atom has a nuclear spin or not. We only know this from the ESR spectroscopy. And so this is direct measurement of a single atom hyperfine interaction. And interestingly here, for the titanium, I showed you we can measure titanium on the bridge binding side and on the oxygen binding side. And so here the grid is all the locations of the oxygen atoms. And so here we're starting off with the bridge binding side, which I showed you before. So we have a certain splitting between these hyperfine states. If I move the atom, or Philip moved the atom to the oxygen binding side, then I see a totally different hyperfine interaction. It's about 4 times smaller than the hyperfine interaction on the bridge side. If I go back to the bridge side, then I go back to the same hyperfine interaction. It's really cool. The titanium we can actually nudge on the surface. We don't have to pick it up and drop it off. We can just kick it a little bit and move it around. So that makes our life a little bit easier here. But the key here is, of course, that the hyperfine interaction is not a fixed property. You cannot say that titanium has a certain hyperfine interaction. It depends on the local environment. And why does it do this? Because the electron is a spin 1/2. It's a single electron in a single orbital. And you can see that this orbital for the bridge binding side looks like a DZ square orbital, but it's in the x direction. So it's a lateral oriented dx square orbital. And if I'm sitting on the oxygen binding side, I have 4-fold symmetry. And then I have something like a dx square minus y square orbital as the lowest energy orbital, right? In both cases, the electron density points towards the positively charged magnesium atoms. So this is actually totally reasonable, and you would expect this. And now it's well known that the dipolar interaction between the electron spin and the nuclear spin depends on the type of orbital that you're in. Right? This is a so-called dipolar interaction between the electron and the nuclear spin, and that is tabulated, and you can look it up. That is different between this particular orbital and this orbital. And so this actually is a measure of the local electronic configuration that this atom or ion is in. Okay, so this is CW spin resonance. Lots of things to explore in this field. Now, finally, I want to show you a little bit about pulsed spin resonance, because this is taking us more towards my ultimate goal, which is quantum coherent functionality. So far, we've talked about CW resonance. So there we apply an RF field, and we usually have a DC bias on as well. But now we want to replace this constant RF field with pulses, certain short pulses of RF, and then maybe we intersperse this with a detection pulse. And here we have a longer RF pulse, detection pulse, and even longer RF pulse. So this is so-called pulsed ESR. And the spin is moving on the Bloch sphere in this Rabi state that I showed you before. This is Rabi frequency. That is dependent on the strength, meaning the RF power, but also on the length of this pulse. So how much time do I give the system to make a rotation? Right? And so this we can do by having a microwave source that has a trigger input, and then we can use a pulse pattern generator or an arbitrary waveform generator to make short voltage pulses, send those pulses to the trigger input of the microwave source, which then goes to bias T, goes to the tip, and so that we can apply short RF pulses, as shown here, to the tip. Right? And the system that we're studying here again is titanium atoms with the hydrogen spin 1/2 system. And so here's the first trace I want to show you. This is now measured at a frequency of 22.57 gigahertz. And we apply now an RF pulse of a certain length. So this x-axis here now is the length of the RF pulse. So in this particular case, we apply 50 nanosecond long pulse, or here it's 20 nanosecond long pulse. And we measure again the same signal. This is always the same signal for us. This is the lock-in signal measured, the lock-in signal, basically the ESR peak. And you can see now we have an oscillation in this ESR peak. We go from low to high, low to high, low to high. And what happens here is that the spin is the spin is rotating based on my driving field from the state 0, the ground state, to the state 1 and then back to the state 0. So here it's rotating from the state 0 to state 1, back to state 0, back to state 1. And of course, we lose some coherence in this process because some scattering happens. And so we see that our overall amplitude is going down. This is the so-called T2 time, giving rise to decoherence in this process. So this is measured for the highest RF power that Kai was willing to put in, 190 millivolts here. If we decrease the RF power, then for the same amount of time, you make a slower rotation here. And so for the same amount of time, you have made a smaller angle change. And you can see this clearly here, that here we have at 50 nanoseconds, we have the second peak. And here, this is at maybe 70 nanoseconds. And here we see the first peak at about 60 nanoseconds, right? So this is all relatively easily understood simply by the driven rotation of the spin on this Bloch sphere plus the T2 relaxation, quantum coherence loss. So that the time it takes us to make a pi pulse here is the time from here to here. That's about 20 nanoseconds. And the T2 time of this particular trace, called the T2 Rabi time, is on the order of 40 or 50 nanoseconds. After 40 or 50 nanoseconds, it seems like the coherence is lost. But we can do much better. And we can do much better if we follow the simple recipes of spin echo. So here you can see the race between somebody who's slow and somebody who's fast. So of course, the rabbit runs much faster here, but now after half the time, this guy tells everybody to turn around. And so when they run back at the end time, they are arriving exactly at the same time at this goal line, independent of how different their speed is in this race. So this is the basic idea of a spin echo. And so what we do here is we have now a more complicated pulse sequence. We first use a pi/2 pulse, then we wait, then we use a pi pulse, then we wait the same time, and then we do another pi/2 pulse to measure the system again. And so what happens then is the pi/2 pulse kicks the system in the XY plane. This is the pi pulse. It flips the spin in the XY plane. And then after a while, it is our measurement pulse. We go back up. And so what happens here is that we can compensate for time-dependent magnetic fields, slowly time-dependent magnetic fields that change during our measurement process. And of course, we're doing this on a single atom. And so you would think that there's no ensemble playing a role here. But of course, we are not doing this in a single shot on a single atom. We're doing this, let's say, 1,000 times averaged for each data point. And so that means that our local magnetic field might be different because the tip height might be changing or something else gives us a local magnetic field noise. And so that's where the spin echo technique helps. And so then here, this is measured now as the free evolution time tau. So both of these together, you can see the ESR signal again as a function of this tau now has an exponentially decaying signal. And now this exponential time constant is about 200 nanoseconds, so maybe 5 times longer than the T2 Rabi time. And so this tells you that the echo sequence here compensates some of the noise that we have. And in particular, we think that this is slowly changing magnetic field noise, primarily coming from the tip, either from the tip moving in height, so some shaking of the tip, or magnetic fluctuations of the tip. And so this is the beauty of a spin echo technique. You can compensate some of that noise. All right, this brings me to the end. I showed you some experimental details of ESR-STM, in particular, a little bit talked about the transfer function and how to measure this. We then talked about electron spin resonance. I'm happy to say now also in Korea, we have 2 systems running at the moment. And then we talked in the end about coherent manipulation of these spin states. And that's, of course, a direction that we want to focus on. And I'll show you in a second why we want to focus on that. So our slogan is engineering the quantum future, and we want to study quantum coherent functionality of atoms and molecules on surfaces. That's really what I'm most interested in at the moment. And so the long-term goal is to not just study one of these spins, but to make entangled states between multiple spins, and then maybe start looking at simple algorithms for quantum computing, and also using this entanglement to do quantum sensing. So this is kind of the direction that we want to go. And for this, we certainly need pulsed ESR, but also multiple qubit pulsed ESR. So that's what's in the horizon for the next few years here at QNS. So we are in, this is where I'm sitting right now. I'm sitting basically here in this office. We have a new building that Ewha Women's University built for us. And Ewha is not an acronym, it's actually a word. built for us. We moved in here 1 year ago. We have about 5,000 square meters. We have a really nice coffee shop, so come and visit us. Eva Women's University is in the center of Seoul, so we have a perfect location about 1 hour away from the airport. 23,000 students and 1,000 faculty, so it's a moderately big university, but kind of centrally located in the heart of Seoul, and a beautiful campus mix of, this is the so-called ECC building. Here's a person. You see this very large building, beautiful architecture mixing old and new together. And with this, I would like to thank a few people. Most of them you see in this picture here. This is all of QNS plus a few visitors. I want to thank Chris Lutz and Kai Young and Bruce Mellior at IBM for our long-term collaboration and also fantastic work we've done together. Also Arjan Ardavan from Oxford University, who is an ESR expert and good friend. And as I said, he was kind of a motivation for us to do ESR-STM. I want to invite you to come visit us. Maybe wait after Corona. At the moment, you have 2-week quarantine to come into Korea. But once this subsides, we really love having people here. We have positions for students open. We have positions for postdocs open, and we have visiting people. Here's DJ. Many of you know DJ. She's currently back here. This was taken last September. She's doing a 4-month research stay with us to look at some superconducting samples. Then we have Hervé from Paris, who's here for 6 months. We really like to have well-trained people come and visit and use the machines together with us. So we have plenty of opportunities for you to come and visit. So with this, thank you very much for your kind attention.
Thank you, Andreas, for this very interesting and very inspiring talk. So now we have time for questions. So if you want to ask a question, you can go to the participants button and then press the more button, and then there's an option to raise hand. So there's already a question by Alex. Alex, please go ahead.
Hey, Andreas, thanks for the talk. There's a small question. This Rabi oscillation you show in this coherence measurement, have you guys checked, exactly. Does that oscillation depend on your DC stabilization voltage at all? Like if you go lower in voltage, do you see the same frequencies?
So the ESR frequency definitely depends on the DC voltage, right? That's set by the tip height, and the tip magnetic field will definitely change that. The RF driving power mostly is set by the RF power that we put down there. And you're asking me if that depends now on the DC voltage. I quite honestly don't know the answer to that. Right? But knowing that everything depends on everything in this field, I would say probably yes. Now, what I should point out here, that maybe what you're going for is that the measurement process here really uses this high frequency detection mechanism called the homodyne detection. And that of course does depend on the DC voltage a little bit, right? But it can also work at 0 DC voltage. So yeah, maybe that's the best I can give you right now.
Okay.
There's another question by Manuel. Manuel, please go ahead.
Okay, can you hear me?
Yes.
Hi, Andreas. Thanks for the nice talk. I was trying to follow which measurements were done on which system now, and I think you showed some Dilfridge measurements now already, or in the iron dimer, iron titanium dimers were measured on the Dilfridge system, or
yes.
not?
The iron titanium dimer was measured on the Dilfridge, but not operating at dilution fridge temperatures.
Okay, that was my question. I think it was measured.
We were just putting in a little bit of mixture, so operating at about 1 Kelvin, which actually is much better for measuring dimers because you don't want to be too cold. Because if you're too cold, the second atom that is nearby is always in the ground state, and so you don't see the interaction energy directly, right? So for measuring dimers, it's actually kind of nice to be a little bit warmer to have some thermal excitations of this second atom nearby. Right? But we have not. We have not done ESR measurements at lower temperatures. First ESR measurements with that dilution fridge are only 2 weeks old.
Okay, so, cool. Yeah.
There's another question by Roberta. Roberta, please go ahead.
Hi, Andreas. Very nice talk. Can you hear me?
Yes, I can.
Yeah. Okay, very, very nice, and particularly appreciated the new experiments on pulsed EPR. I'm wondering, but probably have already reflected on that, you're now making I would say an average, a time average. So in principle, can you exploit the series of pulses that are used for dynamic decoupling? I think that to increase the coherence time, this is commonly done in EPR, and you have actually applied on vanadil vanadil porphyrin in a planar resonator, is something that should appear soon. A publication has been done in Modena, and we have found that when the system is more homogeneous, you have a good increase in coherence time. But for me, that I'm more used to an ensemble of molecules, I cannot shift the experiments to a single spin. So I suppose a train of pulses is not so important for you, or I'm wrong?
So Roberta, the answer is actually pretty simple on this. So the T2 time that we have here is on the order of, let's say, 200 nanoseconds. It takes us 20 nanoseconds to make a pi pulse, I think. And so we just don't have much time to do more complicated pulse sequences. So we've tried this in our Unisoco system. The team has tried this to make more complicated pulse sequences, and it turns out that it doesn't help the T2 time. And this is primarily because we just don't have enough time to make our pulses. So one of the urgent things we need to do is to make longer T2 times. So let's say if we had a few microseconds of time and we had 10 or 20 nanosecond pi time, then we can make more interesting pulse sequences, right? So our next step clearly is to get to longer T2 times in comparison to the pi time.
Sorry, and another question. In the Rabi oscillation, everything of course depends on the strength of the B1 that you are providing. So now you have, it's clearly, it follows the expected law as a function of the voltage. But can this be used to understand what is the mechanism of interaction of the tip? I mean, can you tune the voltage, the distance, so that actually, I mean, you can distinguish between the driving force of the EPR transition?
So I think you pointed this out, right? So you can see here that the VRF gives the strength of this B1 field, of this driving field, right? You can see if we lower the VRF, it takes more time to make these pulses. Yeah. And so this is natural, right? This is part of our driving field. And so in the end, you're asking me, does this help the theorists to figure out which mechanism is actually acting here? And I hope so, but I don't think I'm the right person to now take this and tell you it's this particular mechanism. Right? We often have exchange interaction between the tip and the sample, and we utilize this. So the stronger the exchange interaction is, the better our driving signal is. But quite honestly, we really select our tips to give us good EPR properties, or in this particular case, good pulsed EPR properties, right? And we find many tips that don't do this, and then we just throw them away and we make a new tip. So we really are not doing a good job in that sense to characterize the microstate of the tip, right? We just look at which tip gives us the best signal, and here we look at which tip gives us the biggest Rabi rate for the same RF driving power, and that changes from tip to tip. And so, yeah, that's just tricky.
Okay, thank you very much.
There's another question by Danya. Danya, please go ahead.
Hello, thank you for the talk. And I have a small question. I'm curious about the dipole-dipole interaction to study the titanium and the iron atom. And I was wondering if the effective heights of the moments above the surface could be a problem. For example, if I want to study an unknown property of a molecule which is bigger or is higher than the iron atom, then would it be a problem if I use iron atom to study the unknown molecule?
I would say that is not a problem, but this is a very interesting idea, right? We call that quantum sensing basically. So can we use these spins on the surface to measure something like an endohedrofullerene, like a cage that is 1 nanometer in diameter with some interesting magnetic core? And so the answer is yes, you can. Then you have to, of course, consider the 3-dimensional structure. And you probably have to measure this in more than one physical location. So you have to put many ESR sensors around it, or move one atom to many locations, and then combine all this together. So this is something that we really urgently want to do this quantum sensing on an interesting molecule, and see that maybe we can get a spin configuration that is different from just a point charge, right? That would be very cool. And maybe allows us to measure interesting molecular states that are not just single atoms. So if you're interested in that, come and join us.
Yeah, thank you.
I had one question. So all this stuff was on magnesium oxide. And if I understand Jose's model right, then it suggests that you need a polar substrate. Is this right? Or?
As far as I know, Peter, there is only ESR-STM on 2 or 3 layers of MgO. That may just be because that's easier than other systems, but I don't think that this is unique, right? So at first, when you look at our first paper in 2015, we claimed some fairly complicated symmetry argument why we can make ESR-STM on iron on MgO. This is not true. We don't think that that's true anymore, because we can see ESR on practically every single atom or molecule we put on that surface that has a reasonable spin configuration, like titanium, what else? Copper, also a spin 1/2. Iron, of course. Cobalt, we're not sure. We don't know if we actually saw it. So there are many different spins that show ESR, right? And so I would be very surprised if this is limited to MgO. And one of the things we want to do is try, for example, NaCl, right? Also polar, but not quite as polar as MgO. And I think it should work there too, but nobody has, as far as I know, has shown that yet. So the proof is in the pudding.
Thanks. Okay, I think if there are no urgent questions, so I think what we are going to do now is we are going to stop the official part and stop the recording, and then we'll stay online if there are more questions afterwards. But let's stop the official part here, and thanks Andreas again for a really fantastic talk. That's really nice. Thanks.